Before starting, let me tell you two things, two reminders. One is about the discussion today. So as I mentioned yesterday, the discussion will be only with Nimar Kaniamed on his lectures, because we decided to, since it's on Zoom, we decided to split like that, the discussion. So it will only be with him. And relating to Tuesday, we decided to swap the lecture with the discussion. So at 9:30, you are going to have the lecture, and at 11:15, the discussion. Okay, so it will be updated on the web page soon. So today we start the fifth course of the school with Roberto Emparan, who is going to talk about the physics of near-extremal black holes. Please.
Thank you. Can you hear me? Yes, okay, thank you. So, well, this is going to be, I think, a bit of a change of topic and style from what you had before. This is going to be, there's going to be less string theory and more gravity and black holes. But nevertheless, of course, all of this is related. So we're going to talk about extremal and near-extremal black holes, and there's been quite a lot of interest and developments in recent years. I don't know how familiar you are with already with extremal black holes, but we will go over the basics. So what's an extremal black hole? It's a black hole where there are two horizons, that inner and outer, typically, that there's a limit where they coincide. And when this limit happens, the physics of the object changes. And there's, we will see that there are interesting things like quantum phenomena that become important and that we can treat with control. There are different ways of achieving extremality for a black hole. The most relevant ones are typically with a charge or with rotation. If you have a black hole that has some mass m, and then if it has also some charge, there's a lower bound on the mass for given charge. This is the bound on the mass for the black hole. If you have a spin, then the bound is set in this manner. Of course, this is m squared larger or equal than j, but I'm writing things in such a way that this is units of length. This has units of length, this has units of length as well. In these lectures, I will, most of the time, I will choose the Newton constant to be 1, and the speed of light, of course, always 1. Sometimes I will restore G Newton, and then you will have to figure out what the, I mean, I will do that without warning, and then you will have to figure out that I'm changing units, but it should be simple. Yes. M has dimensions of mass and dimensions of length in general relativity. Gm, that's, I mean, the Schwarzschild radius is 2gm. So when we set a G, h bar is nowhere here yet. So mass has dimensions of length when G Newton is equal to 1. Okay? Yeah. So that's a difference with respect to, well, quantum units, right? If you have a, if you're doing quantum physics, typically mass has units of inverse of length when you set h bar to 1. So in gravity is different, and of course this has implications. We will probably see some of that. Okay. So this has units of length, units of length. The charge will also be measured in units, in geometric units, units of length. That's something that we can always do. We can choose, in general relativity, everything, every quantity that you have should be translatable into units of length, because general relativity is a geometric theory. So everything, every quantity, you should be able to translate into some length scale. Yes?
So we're just going to do asymptotically flat spacetimes here in these lectures, or are we just going to concentrate on asymptotically flat spacetimes?
So it's going to be mostly asymptotically flat. Then we will go from there to asymptotically ADS2, but we will get to that. I'm not going to have a cosmological constant in, say, in 4 dimensions or higher. Okay? Many of the things that we will be saying will generalize to that. So as I said, we can have extremality. Yeah, of course, if we have a cosmological constant, then the bound changes. So this is for Reissner-Nordström black holes. So I will focus mostly on this case, even if the rotating case is also interesting and important. but it's technically more complicated. And many of the things that we will learn about these black holes that are close to charge extremality, many of the things that we will say will also generalize to rotating extremality. Okay, not all of them. There are some differences, not only technical, there are some physical differences, and maybe we will mention them. Okay. Now, when you saturate these bounds, that's when you get, this is the extremal limit. Okay, so these are extremal black holes. Then it's been realized since the beginning of time that these black holes present qualitatively new properties.
Extremal black holes when either m is q or when m squared is j, or do you have to have both at the same time?
No, you can have them separately. So there can be neutral black holes which are rotating, in which case the extremal bound is 1. You can have charged black holes which are not rotating, then the bound is this one. You can have them both rotating and charged, and then the bound changes, and I'm not going to discuss that. So I'm going to do mostly spinless, so this would be J equals 0, spinless charged black holes. Okay. Now, as I said, there's something that was realized early on in these black holes. Well, as you approach this limit, there's a quantity. I mean, you've heard that the black holes have a temperature. We can assign a temperature to them. Then, as you approach the extremal limit, the temperature goes to 0. We will see this. So then, extremal black holes are 0 temperature states. And something very peculiar was noticed from the beginning is that these black holes also have a non-zero area. An area is entropy for a black hole. So it looked like these black holes had a large entropy at 0 temperature. That's a huge degeneracy of states at 0 temperature, and that's something that's unconventional for quantum systems. Okay, you know that the third law of thermodynamics would tell you that the entropy should go to 0 as the temperature goes to 0. And black holes seem to violate this version of the third law. Then, well, that's been understood for a long time, or at least it's been realized for a long time. What did people do about this? Does this mean that black holes are just simply not conventional systems? They are not. They don't follow the laws of quantum mechanics, because in general, you cannot have quantum mechanics prevents you from having large degeneracies, exact degeneracies for ground states. Quantum mechanics tends to, unless there's some symmetry protecting those degeneracies, quantum mechanics breaks that degeneracy, and these states should be lifted. But this is something that, well, these black holes would appear to be violating. Now we've understood what's going on, and that these lectures will be, to a good extent, about that. But it's been a puzzle that's been with us for over half a century at least. Okay? And one of the things, actually, one of the themes of these lectures will be that black holes, now we understand that they comply with the laws of quantum mechanics. That black holes don't violate this version of the third law, that the entropy of a black hole that doesn't have a strong symmetry protection in this case would be supersymmetry, so we won't do supersymmetry, but black holes that are not close to a supersymmetric state, their entropy will go to 0. We will see that. And in that sense, they will behave as other systems in the lab. This will be due to large quantum effects. We will see that close to extremality, black holes behave not as classical systems, but they can undergo large quantum fluctuations. And those are large quantum fluctuations of the geometry. So that's quantum gravity. And then you may say, well, but do we know well enough quantum gravity to do this? Well, in this case, yes. That's what's most surprising about this, that close to extremality, we can do large quantum fluctuations of the geometry with control, with good control. Okay? That's something that we've understood in recent times. And that's without needing an ultraviolet theory of quantum gravity. We will not need a string theory or holography or other things. Even if it doesn't hurt to know string theory and holography, it helps you put things into place. But the things that we will learn will have a large universality. Okay? So even people who hate string theory would need to understand this and take it into account. Near-extremal black holes, we will see that they are theoretical labs for quantum gravity at low temperatures. And this is something that I think it's a new phenomenon, that we can do this with good control. This is without invoking, as I say, Planck scale gravity. Okay? We can have fluctuations of the geometry that are controllable for arbitrarily large black holes. And one important lesson that I always like to emphasize when I'm talking about this is that there's something that you probably, if you've taken courses in general relativity and you've studied the Reissner-Nordström black hole, well, people have explained to you there's the classical extremal black hole and there's a Penrose diagram for it. Well, one of the things that I want to emphasize is that the classical extremal black hole of GR textbooks or lectures, that's an artifact of taking the wrong order of limits. We've been teaching these things the wrong way all along, myself included. The course that I've been teaching in Barcelona, now I'm not doing that. I'm telling my students that the classical extremal black hole is a mathematical artifact that has nothing to do with physics. It has to do with physics the same thing as much as if you want to study, say, the ground state of the classical hydrogen atom. Of course, you can do that. You can prove mathematical theorems about that, but you're not doing physics. At very low energies, for the hydrogen atom, you have to use quantum mechanics. Classical mechanics is useless, close to the ground state. It's the same thing with extremal black holes. Close to the extremal limit, you have to take into account quantum mechanics, whether you like it or not, if you want to do physics. If you first send h bar to 0, and then you take the temperature to be 0, then you get the wrong order of limits. And this is what we've been doing all along. If you have a non-zero h bar, no matter how small, there's going to be a temperature at which quantum effects are unavoidable. Of course, this doesn't mean that we have to throw to the waste bin everything that we've learned about extremal black holes so far. What we have to do is revisit it and reassess it. And that's something that what people are doing these days. Okay? So these are, this is kind of the main playground that we will be in. But there are things that are also around this topic that we won't be doing. For instance, I will not talk about supersymmetric black holes, about BPS black holes or BPS states. It's not because they are not important, they are hugely important. In string theory and supergravity, if you want to have a good control over microstate counting, that usually require supersymmetry, but that's a different topic. There's different physics, and we will not do that. I will not be doing rotating black holes, mostly because of technical complication. Rotating black holes are, they have less symmetry. They don't have full spherical symmetry, so you break some of the symmetry, and this means that solving the equations is a much more complicated affair. Okay? There are some differences in the physics. For instance, the physics of superradiance is different in one case than the other. And then since you have less symmetry, you will have less control over some effects. For instance, we will do quantum corrections and quantum computations for these black holes. And in this case, we can argue that the results that we obtain are one loop exact. That's something that we are not able to do in the case with rotation. Something that we won't be doing either is other extremal objects like p-branes, black p-branes. Black p-branes, when p is larger than 0 or larger than 1 in many cases, those are also important in string theory and supergravity, but they are different. So we will be doing black holes in the sense of objects that are not extended along infinite directions, or like a black p-brane would be. Okay, so they will be spherically symmetric ones. I won't be doing applications to condensed matter theory, even if this is also a place where these things are important, because when you have black holes which are close to 0 temperature, then they are holographically dual to systems, condensed matter systems, strongly coupled condensed matter systems at near 0 temperature, and that's of interest, but I won't do that. And I won't be doing astrophysics. Okay? I will mention something about, well, even if you can have black holes in the sky with spins that are, say, 0.99 from this limit, So they are relatively close to extremality, but we will see that that's not enough for what we will be doing. So of the effects that I will be discussing, there won't be much of a chance of observing this in, say, LIGO or LISA or any upcoming observations of black holes out there. Okay? So what we will be doing instead is, what we're going to do is, today in the first lecture, I plan to discuss the Reissner-Nordström black hole and its properties near extremality, its main properties. Then, well, if I get to finish this today, then next day we will be doing the effective two-dimensional description of these black holes at low energy and their quantization. Then the third lecture will be about the interaction of these black holes with radiation. That will be emission and absorption. Emission, we will see that the original Hawking calculation of emission of a radiation, that will be drastically modified by these effects, by close to extremality. And then the last day, if I still have time, then we will come back to extremal black holes, even if I will have been trashing them around for all the lectures, but we will revisit some phenomena that people have studied in recent decade, something called the Aretakis instability and also tidal singularities. Of black holes in the extremal limit. Okay. I hope that the lectures, so my plan is to send the write-up of these lectures to be posted in the website, so you can follow the write-up and then you don't need to take notes if you don't want to. Okay. So any questions so far? Yes.
So will this be specific to 4 dimensions, or this will be valid in any dimension?
So most of the things that I will be saying, I will discuss 4 dimensions, but everything here can be extended to higher dimensions without, actually almost everything here it has a natural and simple extension to higher dimensions. The phenomena here, particularly these ones, are strongly dependent on the number of dimensions. But the first thing, once we've reduced everything to a two-dimensional theory that describes just the time direction and the radial direction, then the additional space will be just something that comes along for the ride. But I will be only discussing explicitly 4 dimensions, but the extension is simple. So the setup for almost all of what we're going to see in this first part of the course is Einstein-Maxwell theory. Everyone familiar with this Lagrangian, or at least you've seen the Lagrangian formulation of general relativity? Is this something that I see people nodding? Yeah? No? No? Anyone know? Okay. So this is the Einstein-Hilbert Lagrangian. This is the Maxwell Lagrangian. We're putting them together. F mu nu, of course, it's antisymmetric field strength. Okay. As I say, I'm taking units where G and C are set to 1, and we will be measuring, as I said, charge in units of length. The equations that you derive out of this, let me write them out.
Roberto?
Yes?
So you're setting E to some value. E, or alpha. What's the value of alpha?
Of the fine structure constant, the charge in these units. Well, that's always, if we set alpha is, or square root of alpha is 1/10.
Yeah.
That's it. That's the value.
I know, but it's not in the Lagrangian.
Yeah, I've absorbed it. Yeah, so if you want, yeah, that's, I don't remember what the actual number is, but I will not need it because I won't have electrons for most of the lecture. We will return to this, okay? Yeah, what's the, so if I can give you, so that's, let me set also h bar to 1, so I'm using Planck units. Then the electron charge is, as I say, it's 1/10. So that's a pure number. I don't have you can always absorb the electric coupling constant in the, I mean, since I don't have any explicit electrons in my Lagrangian, I don't need to put the electron charge. It's a free theory. I don't need it. Yeah.
Your black holes have charge.
Yes.
So they are like electrons and monopoles in a sense.
So what we will see is that we'll have a potential like this, like the Maxwell potential, and this will have geometric units. So this will be units of length. This will be dimensionless. So that's, I don't need the electron charge anywhere in my equations.
Just, yeah, because...
Yeah, that's, so if I wanted to include a coupling, I mean, this would be, say, something like this, then I would need this explicit. But this would be a pure number also. I mean, it's going to be 1/10 for me.
Just imagining, you know, to make a charged black hole, you have to.
Not necessarily. I can have a charge without charge.
Can you?
Yeah. I can have I can pair create two black holes, one with positive charge and the other one with a negative charge, and there are no electrons present anywhere.
Okay.
So I can have, I mean, if you want the picture, that's a picture that's due to Wheeler. So this would have a charge Q, this would have a charge minus Q. You need the charge to be the source of the lines of force, but here you have lines of force that don't have any source point. So I can have that. Yeah. And then actually in the Schwarzschild, in the Reissner-Nordström solution, you know that if you take a slice of a constant time, then that slice of constant time doesn't encounter any singular source for the electric field. If you know what I'm, yeah. So I don't need electrons. We will have electrons later, but a notion of? A minimum charge.
Minimum value of the charge.
So far, no. I don't. I don't need a minimum value of the charge. I don't have any charge particles still. Later, I will introduce them because I want to discuss some phenomena that appear when you have charge fields. But here, there are no sources, point sources for the charge. This is in my Lagrangian. Here, the charge. If you have a positive charge coming in the geometry, then there will be no point sources for it. Okay. So this is the Einstein equation. This is the stress tensor for the electromagnetic field. You have the Einstein equation, then you have the Maxwell equation. Okay. I don't have any sources here. So we want to analyze these equations and find a solution. Before we go and find the solution, let me begin with some estimates, okay? So you're all familiar with the Schwarzschild solution. Well, this is the unit 2 sphere. Now, this doesn't have any charge. If we now want to add the electromagnetic field of a charge like this one, then this electromagnetic field will have some energy, and this energy will gravitate, and then the gravitation of this energy of the electromagnetic field is going to modify this, this metric. Okay? Can we get an estimate of what it should be? Well, as I already anticipated, we expect that at least at large distances, the electric field, the electric potential is going to be of this kind. Okay? So we're going to have an electric field that will be up to signs on pure numbers. The electric field will be like this. This is the Coulomb field. Then there will be the stress tensor of the electromagnetic field is going to be kind of the square of this. It's going to go like this. Okay? So what will be the gravitational effect of this electromagnetic energy of the charge? Well, the Einstein equation tells you that if you have, these are second derivatives of the metric that you have here, and then you equate this with the stress tensor. So the contribution to the metric, the correction to the metric coming from the electromagnetic field, I'm not putting indices here, I'm just getting an estimate. This should be something like the stress tensor. Okay, so this is what the Einstein equation schematically would give us. So then this means that the correction to the metric coming from the electromagnetic energy will be like Q squared over R squared. And then when we solve the equations, we will see that this metric gets corrected precisely by terms of this order. Okay, so that's just to first hint of what we can expect the geometry to be like. Now, how are we going to solve the equations? Well, we impose a spherical symmetry. We're going to impose a spherical symmetry, and this will help us simplify a lot the problem. So we're going to consider first spherically symmetric fields, then we will particularize to static ones. Actually, if you impose a spherical symmetry, there's Birchhoff's theorem tells you that this will require that the solution is static. That's essentially because the gravitational field is spin 2, and the electromagnetic field is spin 1, so there are no time-dependent S spherically symmetric solutions. Okay? There are no time-dependent S waves. So staticity, we will impose it, but you can derive it once you have a spherical symmetry. So let's consider spherical symmetric fields. And then the analysis, well, I developed in quite a lot of detail in the notes. I will skip some of the things. If you want the details, they are given in the notes. But we will begin writing a spherically symmetric ansatz for the four-dimensional metric, and I'm going to write it in the following manner. If you want to see the motivation for writing it like this, then it's in the rest of the notes. Yeah, dependent also on A. Okay. So this A and B are the time and some radial coordinate index, 0 and 1. We're preserving, so everything depends only, nothing depends on the angle coordinates, it just depends on T and R. XA, like B and C, are these indices. And then, so this is spherical symmetry. We allow for fluctuations in the size of the spheres, or the size of the spheres can change. And this is the TR part of the geometry, which we've written in this manner with this function over here. This is a general form for spherical symmetric geometries. We've written in this form for convenience. Okay, so we have the same factor over here and here. And this is a two-dimensional metric that depends only on these coordinates T and R. Now, when you do this, when you take these ansatz, and you also take an ansatz for the spherically symmetric electric field, then it's easy to solve the Maxwell equations. Yes?
Yeah, I have a question about the action. Why didn't you put covariant derivatives in the definition?
Here.
Yeah.
Yeah, I could put covariant derivatives, but if you want a simple answer is that the difference between the covariant derivative and the conventional derivative is in the Christoffel symbols. They would cancel between the two. A more sophisticated explanation is that this is a two-form, and it is defined regardless of what the metric is. Okay. Okay. So once I take this spherical symmetric ansatz for the metric and also for the gauge field, as I say, the Maxwell equation is easy to solve, and then you find that, well, the Maxwell equations, what they give you, something that, well, what we will need is that f squared, of course, is f mu nu times f mu nu. This will be minus q squared over phi squared, where phi squared is a function that we've defined before. Q is an integration constant that you can identify as the charge by taking the Gauss's law. So you have a spherically symmetric electric field. This is the field strength. And then once you have this, then you can plug this ansatz for the metric into the action. You can compute what is the four-dimensional scalar curvature for this metric, and you express it into the curvature scalar for this metric. And, well, after some manipulations, you arrive, then you integrate over the directions of the sphere. Everything will just depend on the TR directions, the XA and XB directions. And once you've done this, I will explain now this, what's the structure of this and where the different terms are coming from. Okay. So as I said, this is what we get by plugging this form of the metric into this action. We integrate the directions of the sphere. So we get things depending all the directions of the sphere. They've given us integration of the spheres. It's given us a 4 pi that cancels a 4 pi in the denominator over here. So that's integrated. Those are cyclic directions. Then we get here the scalar curvature of, this is the scalar curvature of this metric. It's multiplied by the value of phi, which is phi. You see that this is measuring the size of these two spheres. And then we also have this term that's a potential term for this field phi, for the size of the spheres. Okay? This potential takes this form here. R naught is just some fiducial scale, something that has the dimensions of length that we will fix later. Something that you can choose at will. And then we have these two terms in the potential. This comes from the integration of this term over here. And this, the origin of this, it's essentially coming from the curvature of this of the sphere. Okay, so you see that this Ricci scalar, there's going to be part of this Ricci scalar is going to be the Ricci scalar of the two-dimensional geometry. The other part is going to be the Ricci scalar of the sphere. The Ricci scalar of the sphere is giving us this term. Okay. So we've reduced everything to something that's what's called a dilaton gravity theory in 2 dimensions. Phi, we call it the dilaton, something that measures, well, it's related to dilatation. In this case, it will be dilatation breathing mode of the sphere. And it's a 2-dimensional theory of gravity, okay? And these theories have been studied extensively over the years for arbitrary form of potentials. These theories, that's something that we will discuss later. They don't have propagating degrees of freedom. The reason is what I said before. Okay? These are spherically symmetric sectors of 4-dimensional gravity theory. And as I already mentioned, there's no dynamics in the spherically symmetric sector of gravity because gravity is a spin-2 field. Okay? There's no dynamics either, spherically symmetric dynamics for the Maxwell theory. There's also a Birkhoff theorem for the Maxwell theory, even if people usually don't say it like that. But you've never seen a spherically symmetric wave of the electromagnetic field. And the reason is that, well, as I said, the electromagnetic field is spin 1, which means that the radiation begins at L equals 1. For the gravitational field, it begins at L equals 2, and there are no S waves. So this theory, so it doesn't have any propagating degrees of freedom, but this doesn't mean that the theory is not interesting. It has black hole solutions, okay? And actually, the black hole, the Schwarzschild black hole, is a particular solution of this theory if you set the charge to 0, okay? When you reduce it to 2 dimensions. So you can now derive what are the equations for this theory. You take variations. You take first, you demand that the action is stationary under variations of the dilaton. Then the equation is very simple because here you have this derivative of this and then the derivative of this with respect to the field.
Roberto.
Yes.
How did you choose the powers of phi in the metric?
Good. Yeah. So why did I choose them? You mean these powers? Why did I choose them like this? Okay. The reason is that if I didn't choose it like this, if I didn't put it, it's something that, well, first thing that you do when you do this analysis, and that's how I explained it, say that you define your metric without this factor. Then you get a 2-dimensional dilaton gravity theory, which is perfectly fine, but it has a term, an additional term that would go like this. And this is fine. There's no problem with this. But you can eliminate this term by performing a redefinition of the field. This is a Weyl rescaling of the field, and when you do that, you get rid of this term. And then your action becomes simpler. Okay, so you don't get this sort of a kinetic term for the field. It's not a real kinetic term, because as I said, there's no dynamics in this sector. Actually, this comes with a wrong sign, so you might worry that it would be a ghost. It's not a ghost. It's simply something that you can remove by a redefinition of your fields. So the reason for this is to get rid of this. And that's, as I say, I explained that in detail in the write-up of the lectures, okay? So it's a valid point, because you may worry that. So the way that I derive it is I begin with some other metric. That's why this one got a bar in particular. You begin with this, and then you arrive at a theory that has this term, and then you say, well, I want to remove this term, I perform the rescaling, and then I determine what the power has to be, okay? So, good, thank you. So that's the equation that you get from varying this. Then the equation that you get, so this would be, say, the dilaton equation. The gravitational equation, the metric equation, is what you obtain by requiring that the action is stationary with respect to variations of the metric. That's a little more complicated, but it's not too difficult to obtain it. Okay, so this is the equation. And here you see that even if this is the variation with respect to the metric, there's something that's missing. We don't have the Einstein tensor anywhere. We don't have this term anywhere in our metric. So what happened to that? Actually, when you do the derivation, you do find a part that's like this, but in 2 dimensions, this is always 0. That's an identity. Okay? For those of you who know, this is because the Einstein-Hilbert term in 2 dimensions is a topological term. Okay? So this is identically 0, but nevertheless, having the dilaton gives us non-trivial equations. That's the reason that when you want to study 2-dimensional gravity, if you started with, if you start with this action, this doesn't give you anything, at least at the classical level, that's of any interest, because this is just a number that's independent of the details of the local geometry. It only depends on the topology of your 2-dimensional manifold. Okay, so this wouldn't give you any interest in local physics. When you include the dilaton, then you get a non-trivial equation, okay? One that you have to solve. So now you want to solve these equations. This one you don't have to solve. That's already automatic, but you want to solve these 2 equations. To solve them, well, as I said, you can do this, you can prove that the solutions have to be static. I'm not going to do that. I'm going to instead assume staticity, something that says it can be derived. But let's assume that things depend only on one of the space directions, the radial direction, we call it. And then we write down the metric, this 2-dimensional metric. We write it like this. Okay. Well, R naught is, again, this fiducial scale that we will fix later on. Okay. So this is, you can always choose this form of the metric. This is a general static spherical symmetric ansatz. The radial gauge hasn't been fixed. We can choose our radial gauge, our radial coordinate. We can fix it in an appropriate way, in a convenient way. And what we will do is we can fix the radial gauge so that phi is r squared. So we define r, if you want, to be the square root of phi. That's a choice that we can always make. Once you do this, your equations simplify. And the Einstein equation, this one, this first equation, the TT component of the equation, this gives you sorry? Phi?
Why is phi a function of r only?
Because I decided to do that.
Okay.
I decided to go for static configurations.
Okay, okay.
Okay, so it doesn't depend. I assume that there's a time like killing direction. I call that T, and then everything will depend only on the radial direction, and that's by design. I could prove that, but it will take me a little longer. I could prove that there cannot be any time, that there has to be a time like killing vector, but I'm not doing that. So the TT equation here, if I set indices TT, then this becomes this equation, which is simple to solve. This gives me 1 plus C over R plus Q squared over R squared, where C is an integration constant. This integration constant, by looking at the field at large distances, this identify as the mass. Okay? Yes? Yes, over here.
Do you get phi equals r square by extremizing with respect to phi, or is that a choice of gauge or something?
Sorry, say that again?
The phi equals r square, do you get that by extremizing with respect to phi?
No, this is a choice of my coordinate. I can choose my radial. You see that I can redefine my radial coordinate here. It's something that I can, nobody tells me here what r should be. I can always choose it such that it satisfies some condition. That's the condition that I want r to satisfy is that r is square root of phi. That's something that I can do.
But you still want that to obey the extremization condition with respect to phi,
Yes,
right?
but I still, yeah. So I will apply this this condition later, but this is something, it's just a gauge freedom that I still have, or the coordinate freedom that I still have in my system, and I'm fixing it in this manner. Okay. So as I say, this equation, I can take the TT component and solve it like this. I get an integration constant, this integration constant by looking at the field at large distances. If you compare it to the Schwarzschild solution, then I identify this C as minus twice the mass. And then the RR Einstein equation, that's then you can also plug it here, and then you solve it. Then you determine that the function f has to be some other constant, integration constant, times the function g. So this is the other equation. This constant, you realize that this is something that you can absorb in a redefinition, a rescaling of t. So I can set C2 to 1, because it's something that can be absorbed, as I say, in a rescaling of time. Okay? And once I have this form of f and g, you can verify that the third equation is also automatically satisfied already. Okay? So then, I found the solution that I wanted. So I found going back and doing the change that is, so I went to 2 dimensions, now I'm going back to the 4-dimensional metric. This 80. Okay, so this is the Reissner-Nordström solution. Okay. I will go I've done this reduction to 2 dimensions because this will be useful later. Okay. The solution that it's been known since 1919 or something like that. Okay. And you see that we have here the correction that comes from having a charge, from having an electromagnetic field with some energy that gravitates. This correction to the metric is precisely of the same kind that we already anticipated. Okay. So the term minus GTT, let's examine this a little bit. Notice here that here we have a minus sign, and here we have a plus sign. The minus sign, this is what's telling you that gravity has an attractive effect on particles moving on this field. Okay? So that's conventional. But then here you have a plus sign. GTT, you know that this is a kind of the relativistic version of the Newtonian potential. Okay? So here we have the Newtonian potential, 1 over r, with a minus sign, attractive effect of gravity. This has a plus sign. So it looks like the introduction of this charge, of the electromagnetic field of this charge, is having a repulsive effect. A repulsive effect also on neutral particles, because this is the gravitational interaction. Is it true that the electromagnetic field has a repulsive effect? No, it cannot be. The electromagnetic field satisfies all of the energy conditions that you might want it to satisfy. So why does this seem to have a repulsive effect? Well, the explanation is simple. M here is the mass that you measure of the entire system when you go to infinity, okay? So we have here, we will see that we have a black hole. You have some object here that's creating this field, okay? And then at large distances, you are an experimentalist, and then here you have your, I don't know, your dynamometer or whatever you use to measure the gravitational field with your unit mass. And here you measure a mass m. And this is the mass, the energy of everything that's inside this sphere. Okay? Now say that you move some distance inside. And then you're not at infinity, you're at some radius r. And then you perform this experiment, and then here, the gravitational effect is the gravitational effect of only the stuff that's inside the sphere. So the electromagnetic field outside the sphere doesn't contribute to the gravitation of all the system. Okay? So we can define an effective mass at this radius as the total mass minus the energy of the electromagnetic field in the sphere outside R, or in this shell outside R. That electromagnetic field would be like this. Okay? So then you can write now like this. This is the effective mass that you perceive at radius r. And you see that this is the same as this. So it's not that there's repulsion. The electromagnetic field, it doesn't create a repulsive gravitational field. What you have is less attraction. Okay? Less attraction looks like repulsion. There's no morals involved here. Okay? But that's the explanation for the plus sign. This plus sign means that as you move to smaller radii, then you feel less attraction, because you have less energy attracting you. Okay? Now let's analyze this function, this potential, a little bit more. Okay? Well, first, this metric has things go bad at r equals 0. R equals 0, you can verify that that's a singularity, because this goes to infinity when r goes to 0. Okay? The scalar curvature doesn't diverge, it's 0, because the stress tensor of the electromagnetic field is 0, but this goes to infinity. This is a scalar quantity, so you cannot change it with coordinate definition, so this is a true singularity. Okay? But then there are other places where this metric shows this metric coefficient shows funny behavior, and those will be horizons. For a static solution, you can look for horizons as places where the potential vanishes, where you have infinite redshift. This corresponds to having the function that we had over there, f equals 0, and this happens. You have to solve this to be 0. That's a quadratic equation. Okay. So this will be real whenever m is greater or equal than q. I'm assuming that m is positive because I want my energies to be positive. I can assume that the charge is positive because at least in the metric, it appears only with a square. If I'm interacting with particles, then I can always choose the sign so that this will be positive. Okay? So there's no loss of generality.
Sorry, I have a question.
Yes.
So what happened to this effective mass? I mean, is it, I guess, not always positive? At some point, it becomes 0 and then negative. Where is it?
Outside the black hole, it's always positive. If you go inside, yeah, it can be negative.
Is
So
it
then this means that
at the first horizon or at the inner horizon?
So we will see that, well, when you go close, for instance, there's something funny, for instance, the inner horizon or even the singularity, the interior singularity, if you want to fall into the singularity, you have to accelerate towards it. It's repulsive. There's an effective repulsion. So, yeah, and that's something that will be manifested elsewhere. So, yeah, you can have outside the horizon, everything will be fine. Good. Inside the horizon, you can find funny effects, but most of those effects are actually non-physical because of things happening inside the horizon will change the picture. But yeah, in principle, in the interior, you can have the inner singularity is repulsive. Gravitational repulsive, yes.
So when we generally write the action for asymptotically ADS black holes, we generally add a boundary term as well, right, to the action.
Yes.
Why did we not do that here?
So I haven't done so the action that I've written, was written here, didn't have any boundary terms. It didn't have the Gibbons-Hawking-York boundary term. That's because we're not doing anything with that. I mean, we're just deriving the equations or using the equations. In order to derive them properly, you have to add that term. We will get back to this point. Of course, that's important. If you want to compute the action, of course, the Gibbons-Hawking-York term is crucial. If you don't, but at the level of what we're doing, of equations of motion, this is enough. Okay. Yeah. So this action will have a boundary term, and this will be hugely important when we want to consider quantum theory in particular. Okay? So this is real only for when m is larger or equal than q. So we can discuss different cases. We can first discuss a case where m is less than q. This quantity then, GTT or minus GTT, is always positive, which means that there's no horizon, and then the singularity that you get is naked. For those of you who are familiar with Penrose diagram, the Penrose diagram is like this. So there's a singularity that you can see from afar. This doesn't mean that this entire solution is bad. It's simply that the place where the singularity is will be resolved by quantum electrodynamic effects. I see that I'm going much more slowly than I thought, but let's now consider the case of m larger than q. In this case, you have two roots, which are real and positive. These will be horizons. You can verify that you can always take coordinates, Eddington-Finkelstein type of coordinates, which are smooth at the horizon. So these are inner or outer and inner horizons. They're Killing horizons. We can compute their surface gravity, kappa. Surface gravity is a measure of force. So if this is potential, the derivative of the potential gives you a force. This is what we call the surface gravity, the horizon, the derivative of this potential. This gives you an idea of the field strength, the gravitational field strength at the horizon. And that's, where do we have this? And here you see that the surface gravity for the inner horizon is negative, reflecting what we were saying before. That's a repulsive surface. Okay? You have to accelerate in order to get to that. Then finally, there's the borderline case where m equals q. And this is what we call the extremal black hole. As we said, we have these two horizons coming together. because you have R plus equals R minus equals M equals Q. Okay? So you have a double root. The double root, of course, this is what means. It means that this derivative is 0. Okay? This is what we call also a degenerate horizon. It's a degenerate limit. And this is, gives you the lowest bound on the mass for a black hole of a given charge. There's one property of this horizon, and it is that it's at an infinite space-like distance. What do I mean by this? Say that you consider a section, constant time section in the geometry, and the geometry is like this. This function here, when m equals q, this function has a double root. And then if we measure what's, say you want to measure the distance from some radius outside the horizon down to the horizon, so you start at r larger than m, and then you go to r equals r plus equals m, and then you go along a radial line, you fix the angles, you measure what's the proper distance here. Proper distance is going to be the square root of this. This, at r equals m, this has a log divergence. Okay? So then this means that these horizons are at infinite space-like distance. And this geometry, we can draw it in the, this is a three-dimensional geometry, space-like geometry. When r goes to infinity, this becomes flat. This is what I'm drawing. At the large distances, this becomes an asymptotically flat geometry. But when r goes close to r equals m, then this becomes you get a geometry like this. Here you have that these spheres reach essentially constant radius. So these are circles. These circles correspond to these spheres. These spheres, when r goes to m, so this is r goes to infinity, that's flat. R goes to m, we get that this distance diverges. Here it's okay. So when r goes to m, this diverges, and then we get what we call an infinite throat. Okay. So when we talk about throats in these geometries, this is what we're referring to. As you get close to extremality, then the spatial sections of these geometries, they develop longer and longer throats. Okay. These throats, we will analyze the geometry of them. But here you have these throats of constant curvature, and then we also have a two-sphere of fixed radius. Okay? And the fact that these throats go infinite in this limit, it's what makes this one of the properties of these systems that make them super sensitive to effects like quantum fluctuations. Questions? How many of you have seen all of this before? Raise your hands. Yes. Okay, so many of you. Sorry. How many of you haven't seen this before? Okay, still a few. Yeah, there was a question on somewhere. Yes?
Hi, related to the previous question that Francesco had asked, if I have an extremal black hole, then the effective mass goes to 0 at the horizon.
Yes, that's
is that like a statement that the extremal horizon is kind of fake, or is it?
No, it tells you that something funny is happening there. This notion of mass, it can be more properly characterized as something called the Komar mass. The Komar mass would vanish, it vanishes at the extremal horizon. And that's something that I can define in a covariant way, in a more rigorous way. Doesn't mean, what it means is that, if you want, that all of the energy, that black hole doesn't, all of the energy comes from the electromagnetic field.
Right, I see.
Not from the black hole itself. Tells you that something fun is happening.
Yeah, thanks.
That's, I think, the best thing, yeah, I can say. Okay. We're going to do now thermodynamics. Some of you are probably familiar already with black hole thermodynamics, but I'm not going to derive thermodynamics. I want to use is the fact that we know, since more than 50 years ago, that black holes can be assigned a temperature that's proportional to the surface gravity. There's a factor of h bar here that I'm not putting. Because surface gravity, this has dimensions of acceleration, that's inverse of length. You multiply it by h bar inverse of length, that's an energy, and temperature has dimensions of energy. Okay? So this is, black holes have this temperature, so they emit radiation at this temperature, as Hawking showed. This is 1 over 4 pi Fr prime, and I'm only going to consider in these lectures the outer horizon. You see that in the extremal limit, the temperature of the black hole goes to 0. Okay? We can also assign a potential. This phi now here will be the potential. There's not enough phi's in the Greek alphabet. But this is the potential at the horizon. This is Q over R plus, which is square root of R minus over R plus. And then we also have an entropy that's proportional to the area. Of course, G Newton would set it to 1. This would be this. Okay. The mass, by the way, in terms of this, it's very often convenient to use as your parameters R plus and R minus. If you're going to do calculation, better than using Q and M, it's more convenient to use R plus and R minus. Q would be, okay. So you can say that your solution has two parameters, R plus and R minus, and its energies and other properties are given by this. You can verify that they satisfy the first law. Okay, so this is satisfied. The easiest way to do it is to take derivatives of these quantities. So you take here these variations with respect to R plus, with respect to R minus, and then it follows easily. Okay. And in the extremal limit, where these two things are equal, then you see the temperature goes to 0, the potential goes to 1, but the entropy, this is the Bekenstein-Hawking entropy or black hole entropy, this goes to pi q squared, and this is different than 0. And this is a puzzle, because as I said, we want to interpret this entropy as measuring some number of states of a black hole. So typically what we would say is that if we have a system with this entropy, then the number density of states at a given energy, so let me draw it like this. So I'm going to, yeah, okay. The number density of states of the black hole, I'm going to draw here m minus q. So this is the energy above extremality. Then what this picture seems to be giving us is something like this. So at large energies, certainly in general, you expect that the density of states, number of density of states, is going to be the exponential of the entropy, okay? So if you have a system with this number density of states, the log of the number of density of states, that's the entropy. So Bekenstein and Hawking would tell you that this system would have this number density of states, but what we find here is that in the t, the limit where t goes to 0, you have a number density of states that's non-zero. For a macroscopic black hole, the entropy is large because the entropy is area measured in Planck units. If your black hole is very large in Planck units, then the entropy is very large. The exponential of a large number is a huge number. So then this means that at 0 temperature, you have a huge number of a huge degeneracy of states. And that's something that if there's no symmetry protecting that degeneracy of states, that's something that quantum mechanics doesn't like. Quantum mechanics likes to break degeneracies whenever possible. Okay? So this is something that's worrisome, and it's been with us for 50 years. There are other properties. So this is telling you that black holes close to the extremal limit, certainly the non-supersymmetric ones, they don't seem to behave as conventional systems. Okay? So there's something here that black holes seem to be very unconventional systems. There's even more puzzles. If we go not to extremality, but we go close to extremality, okay? So now we consider that m is not q, but we want to consider it slightly larger. I'm going to write it like this: m squared equals q squared plus some small number where epsilon is much less than q. Then in this case, r plus minus rq plus minus epsilon. So the two horizons are separate. They are not the same, but they are close by. If we expand all of these quantities for small values of epsilon, then we find t is linear in epsilon. I defined actually epsilon so that this happens. So I can, instead of epsilon, I can use t. Epsilon is 2 pi squared t, up to small corrections. And then the energy above extremality this is, of course, Q. This is the energy that I have available in my system, the energy that's not fixed by the charge. This is so this is how the energy behaves as a function of the temperature when we're close to extremality. And this is the energy above the ground state, okay? The minimum energy state. So this E, I'm going to write it. This EB, this quantity EB, then label B will become clear later. This is an energy scale. That's if I restore G Newton, this is going to be G over Q cubed. Okay. This is this Q cubed. I can also write it in terms of the entropy. Like this, okay? This is a number, since the extremal entropy is a very large number, this is a number that's much smaller than the inverse of the black hole radius. So this is an extremely small scale. I will say more about this in a moment. But this scale will be relevant in everything that we will be saying later. Okay? But you see that that's, if you have a black hole of some size, the characteristic energy scale or that's associated to that, it's going to be the inverse of the radius. But here we have another scale, which is much smaller than that, that scale. Okay? We have two different scales. That's because of the very long lengths that the system has. Okay? For a black hole close to extremality, this throat won't be infinite, it will be finite. But we have two scales. One of them is the radius, and there's another scale here that's going to be the inverse of this energy, and that's much larger than 1 over R plus, than R plus. Okay? So these black holes come with two separate scales. One of them, the one given by the width of the throat, and the other one by the length of the throat. This separation of scales is what introduces all the new physics here, because we can have different physics at this scale and at this scale. So physics operating at each of these two scales will be different. And one, and I will finish now. One puzzle that this relation poses, it was realized in the early 90s, is the following. So let me draw here the energy, that's the energy above extremality, as a function of the temperature. Okay? So what we're saying is that this energy goes like T squared. Okay? That's the energy that you have available to, for instance, emit radiation. So a black hole that has some, that's in this regime, it will have some temperature, and then Hawking would tell you that this black hole will emit radiation with a thermal spectrum given by the temperature T that we had. So then this means that the typical energy of a Hawking quantum would be linear in T. Okay? And this diagram, this is something that tells us that something is going wrong here. If we have a large temperature, then this is the energy, available energy, okay? Available energy to emit radiation. And this is the typical energy of quantum of radiation. If you are at very large temperatures, everything is fine, you have a lot of energy, you emit one quantum, and that's a small perturbation of your system, a small disturbance. Okay? You have lots of energy, emitting one quantum, that's fine. That's a situation where we can do normal thermodynamics. Small fluctuation, emission of a Hawking quantum, it's a small fluctuation in the system. But once you get to this scale, and this scale is of the order of this energy, then you're in trouble, because here you don't have enough energy to emit a single quantum, typical quantum of temperature T. So Hawking's calculation can't be right here. You don't have enough energy to radiate with a thermal spectrum. The emission of a single quantum here, a single quantum of radiation, is going to have a large effect on your black hole. It's not going to be a small perturbation. So in this regime, for temperatures of this order or less, semi-classical thermodynamics will break down. You have large fluctuations. The emission of a single quantum is a large fluctuation. So thermodynamics, the thermodynamic limit breaks down. It's that you won't have ensemble equivalence. The canonical and microcanonical ensembles won't be equivalent. Also, the Hawking calculation for emission of radiation can't be right. You don't have enough energy to emit thermally. Hawking's calculation is based on semi-classical quantum field theory in a fixed background. So semi-classical QFT breaks down. We expect large fluctuations, large quantum fluctuations. Okay? And this is what the next lectures will be about, how we can even if these fluctuations become large, we can still treat them with good control. Okay? So I'll stop here, and then we'll continue next day.
Some urgent question before coffee break?
Hello. So till now there is nothing quantum here, right? Or till now you have not discussed anything quantum here.
No quantum, but I'm anticipating. Well, I've discussed a little bit. Some quantum is already here, because as I say here, we have an H bar.
Okay.
So when we go from classical gravity to thermodynamics, you have to introduce H bar.
Okay.
And then we're assuming that, well, there's going to be radiation, because Hawking told us that there would be radiation. That's a quantum radiation.
Okay. Okay. Also, the m perturbation to m that you're given, m square is equal to q square plus epsilon square, not m is equal to q plus epsilon.
Let's say that again?
So the m square is, yeah, that's one.
Yes.
Why did you do it for m square, not just m?
Yes, because I want this relationship to come out like this. That's nothing big, yeah.
I don't get how this EB is a new scale in your geometry. I would guess it would still be parameterized by R plus.
So you have two scales in the geometry. That's already clear at the classical level. You can take these two scales. So the black hole has, you can choose them in different ways. But the classical black hole has this radius, and it also has, this is also something that has dimensions of inverse of radius. And near extremality, these two scales, so R plus is much less than 1 over kappa. Okay, so I have two scales. Just because, well, I have a two-parameter family of solutions, M and Q. So I can take one of the scales to be M, that would correspond to this. And then I can take the other parameter to be M minus Q. And when M minus Q is very small, then that's
It's when you step away from the extremal limit that you have this. Okay.
So it's essentially because you have the two parameters. It's the same thing also with rotating black holes. You have M and J, and then you can go to regimes where the two quantities are very different.
Okay, maybe let's postpone the question to later, or you can ask during the break, because we need to use the time for question to Lara later, so let's stick to the time. So let's try to be back at 11:15 on time, so because we have a kind of long day. So thanks, Roberto, again.